Okay. Good morning, everyone. Welcome to this installment of the European American Wind Energy Seminar Series. This is part of a project that Jakob Mann has configured, and I'm one of the hosts of this particular one. I'm Sue Haupt from NSF NCAR, and I would like to introduce today's speaker. Today, we are lucky to have Sarah Pryor, speaking on wind turbine blade leading edge erosion. Sarah is a professor in the Department of Earth and Atmospheric Sciences at Cornell University and an affiliate professor at the Danish Technical University. She is a fellow of both the American Meteorological Society and the American Association for the Advancement of Science. Sarah is on sabbatical this year. I was fortunate to have her visit me in Colorado in the fall, as well as she visited NREL as well. And now she's visiting DTU. And of course, Sarah is well known for her research in leading edge erosion. And we're looking forward to hearing more about it today. Sarah, you have the floor.
Thanks very much, and thanks to everybody for spending time with us today. So just to make sure we're all on the same page, when we talk about wind turbine blade leading edge erosion, we are talking about mass loss. So if we look at this photograph on the left-hand side here, you can see it's a wind turbine blade, and you can see that there has been mass loss from the blade, so we start to see the underlying structure. So as a very crude sort of intellectual framework here, we can think that a wind turbine blade typically has some kind of wooden structure on which is laid glass fiber or carbon fibers with resins that form the real structure of the blade. Then there's a layer of putty, and then there's a coating. And the critical point is this coating is to protect the underlying fibers that are themselves pretty readily eroded. So when I talk about time to erosion, I'm really saying time to the point at which the coating is removed and we start to get mass loss of the underlying material. This matters because if you think about a wind turbine blade, it comes out of the factory and it's aerodynamically perfect. So you're getting maximum lift and minimized drag, so you get most power production. If you start to get this kind of roughening of the blade surface, you get an increase in drag, a reduction in lift, so you sacrifice power production or you lose power production. So in this table here, I'm trying to show different levels of erosion, going from one where perhaps you might see a few pinned holes in the coating down to where we've totally lost the coating at level 3, and we start to see substantial reductions in annual energy production. So obviously that reduction in annual energy production means that revenues decrease, and we start to need repairs in order to improve aerodynamic performance and, quite frankly, enhance structural integrity. And you can see, obviously, those costs of repair start to really increase as we get more and more damage to the blades. So ideally, we'd like to reduce that amount of damage. So really, there are two activities that we're involved in here at Cornell that link across the Atlantic, so that have Danish and US collaborations. The first is a National Science Foundation global center that we run, that you can see the Danish Technical University and also Ørsted are part of here. And this global center has this lofty goal of reducing blade damage, further increasing wind energy reliability, and reducing costs. Pretty high and worthy goals. They are really mirrored within the IEA Wind Task 46, which is has the operating agent of DTU, and that Cornell is part of. So when we think about wind turbine blade leading edge erosion, fundamentally we can think about it as comprising 4 linked themes. The one that I'm going to focus on today, which is the atmospheric drivers of leading edge erosion. So what causes this damage? Theme 2 is linked to damage detection and quantification. So essentially, how can we quantify whether we are currently in damage severity 1, where probably action isn't needed, or damage level 3, where probably repair is necessary and necessary in fairly short term. Theme 3, which is a area of great strength at DTU, is materials response and redesign. So as these hydrometeors hit the blade, what happens in the coating and the substrate? What are the von Mises stresses that are being induced? And then last but not least, there's the aerodynamic implications. So how do we go from damage to understanding how much power we are losing? So without further ado, as I say, I'm going to focus on theme 1 because, as Sue already said, I'm an atmospheric scientist. So if we step back, we can say blade coating lifetimes. So the length of time that the coating will be maintained and will protect the underlying structures to the first order is a function of the kinetic energy that's transferred between falling hydrometeors, so rain droplets, hail droplets, and the rapidly rotating wind turbine blades. So just to give you a sense here, this outer third of the blade that moves, of course, most rapidly dominates power production. So it's also the area of the blade where not only is damage most likely because the closing velocity is highest, but it's also the part of the blade that once its aerodynamic performance is compromised, is most likely to reduce power production. So if we want to know this kinetic energy transfer, then of course we need to know the closing velocity between the falling drop and the blade tip. So that's going to be a function of the hydrometeor fall velocity, which, as we all know, is determined by its diameter. The blade rotational speed, which is, of course, a function of the incident wind speed. The number and mass of collisions, which is linked to the precipitation intensity. And, of course, the hydrometeor phase. I'm not going to talk too much about this, but there is some evidence that hail is a particularly important damage vector. Fundamentally, of course, we can cast this in the framework of the levelized cost of energy, where we can say, of course, the levelized cost of energy per megawatt of electricity produced is a function of capex costs, operations and maintenance, and then, of course, AEP. So if we think about leading edge erosion and how we might want to mitigate it or extend our blade coating lifetimes, we can really think about 3 options. One is we can redesign the blades. So there's some really exciting material science questions here. So for example, is it possible to use flax to increase the durability? Even diamond coating, is that possible? Whatever we do in terms of blade redesign, of course, is going to, at least in the short term, increase capital expenditure costs and doesn't help us with the tens of thousands of wind turbines we already have deployed. So option 2, we can use leading edge protection products. So these might be tapes that we apply to the coatings, or it might be molded, soft or hard mold. We can do that either in mold when the blades are being built or as an after service addition. If we do it in mold, again, it'll increase capital expenditures. If we do it after blade production, it drives up, of course, operations and maintenance costs because it's expensive to add something to an operating wind turbine. Almost all leading edge protection manufacturers will admit you change the shape of the blade and therefore you reduce its aerodynamic efficiency. So if we add leading edge erosion protection, we reduce power production because we're changing the aerodynamics of the blades. Third option is using what we call erosion safe mode. So this is an idea where you say, if I know that the next few minutes are going to be linked to highly erosive conditions, then I simply slow the rotational speed of my blades or stop my turbine altogether. And because the closing velocity between the hydrometeor and the blade is really largely dictated by the blade speed, I reduce that, so I reduce the material stresses. Of course, I'm compromising power production. So our work starts from the perspective of saying, if we want to help owner operators do cost benefit analyses of options 1, 2, or 3, we would like to quantify for them the amount of material stress or coating lifetime in a particular location, and also the probability density function of material stress. So is it concentrated in a few minutes per year, or is it spread out across the year? And we'd like to know when that maximum stress occurs. Is it when electricity prices are actually pretty high, in which case that would feed into greater revenue losses if we go to operation safe mode. So from an atmospheric scientist's perspective, I'm trying to do the best job I can to sort of quantify these atmospheric drivers and aid the industry in terms of thinking about these different options. So if we go back to this idea that we've set out where we say the kinetic energy that's doing the damage, or the force that's doing the damage, is dictated by the closing velocity between the hydrometeors and the blades, the number and mass of collisions, and the hydrometeor phase. We all know as atmospheric scientists that things like, for example, the droplet size distribution is really strongly related to rainfall rate, and rainfall rate is really strongly related to the measurement interval. So this is just a reminder that if we use the mass-weighted median diameter and we plot that, it's just for a site here in the Southern Great Plains, against rainfall rate, that of course droplet size, or average or representative droplet size, increases with rainfall rate. So when it's raining more heavily, we have a few more droplets, but mostly we shift to larger diameters, so they're more massive, so there's more erosion. This figure here just reminds us that if we take 1 minute data, then again at this site in the Southern Great Plains in Oklahoma, 10% of 1 minute rainfall periods have a rainfall intensity of more than 4.5 millimeters per hour. If we were to average that even up to 10 minutes, you can see it halves that most intense rainfall rate. So I'm trying to persuade you here that we need high frequency observations in order to capture the erosive characteristics. So in the first part of this talk, I'm going to present to you a erosion atlas that we've released for the contiguous US, and it's based on the 883 ASOS automated surface observing stations across the US. So in these B and C panels, you see the location of our National Weather Service ASOS observing sites. And I've simply plotted here the annual precipitation, which of course has a strong west-east and north-south gradient. And then the bottom axis, bottom figure here, sorry, it reminds me to say the wind speed measurements are taken at 10 meters. So I extrapolate those up to hub height, using a power law. Then just as a sort of sanity check that that's gone okay, what I've plotted here is the probability that a wind turbine that's the WindPack 3 megawatt reference turbine is operating at its maximum RPM. And this is the 5th to the 95th percentile here. So it's just reminding us that wind turbines in the Great Plains are indeed frequently at rated rotational speed. In the top panel, the black dots show the wind turbines that are operating in the US at the end of 2023. And I've just overlain here the annual frequency of significant hail events, just as an aid memoir that I'm going to come back and say that our erosion estimates for the Southern Great Plains may be underestimated because we do not explicitly treat the action of hail. So how do we do this analysis? So I've started by taking 18 years of observations from each of these ASOS stations. And for each 5-minute observation of wind speed at 10 meters, I use a power law to extrapolate it to the hub height of this WindPack 3 megawatt wind turbine. So we've used the WindPack 3 megawatt because it's almost exactly the rated capacity of an average wind turbine in the US. And its characteristics are public, so we can know its RPM curve, its power production, and also this tip speed as a function of the hub height wind speed. And of course, we need that tip speed because we need it for the closing velocity. In each of these 5-minute periods, I take the 1-minute observations of precipitation. And if any of those 1-minute periods has more than 0.25 millimeters of precipitation, then I compute a 5-minute rainfall rate to link to this 5-minute wind speed. I then, because the coating lifetime model that I use is the multi-layer Springer model, which requires droplet size distributions, I then take that rainfall rate and convert it into a number of droplets of different sizes. So that's what's shown in panel C here, where we've got 2 different droplet size distributions that will be very familiar to the atmospheric scientists. The first one is Marshall-Palmer, and I'm simply showing here for different rainfall rates what the number density of droplets of different sizes are. So I can say for a 2 millimeter droplet, how many of those are available in a cubic meter of air, and this per millimeter is just our normalization. So we are taking care of the bin width, if you like, the range of diameters. In the engineering community, the droplet size distribution that's most widely used is, as you know, the best size distribution. That's not a quality statement. The person who suggested it, their name was Best, and I can quite frequently wish their name had been perfectly ordinary. But you can see here the 2 different size distributions do generate, for the same rainfall rate, different droplets concentrations, and particularly Best, and we'll come back to this, tends to give a higher number of larger droplets than Marshall-Palmer. Once we have the droplet number density, we apply the terminal fall velocity from Gunn and Kinser. So for each diameter, we know how rapidly it's descending in the atmosphere. And once we have those things, we have the hydrometeor number of impacts, diameter of impacts, and closing velocity in each 5-minute period. We feed those into a material science model. It's called the Springer model. It relies on us stating a number of blade coating parameters. I'm not going to dive too deeply into those. We've set those to be fairly conservative, so we're not overestimating damage. So if anything, we're saying the coatings are pretty good. At each location, each 5-minute period, I come out with what we call the accumulated distance to failure. So this is saying how much of my blade coating lifetime have I exhausted? I integrate across each diameter and closing velocity to say, okay, now accumulating everything in terms of its full velocity, closing velocity, and diameter, I can say in this 5-minute period, how much total blade coating lifetime was exhausted. And this is a cumulative probability distribution that shows us that actually, if we look at the accumulated distance to failure, so this is in each 1-minute period, our most erosive events, 1/1000th of the coating lifetime is exhausted. You can see this is a pretty sharp cumulative distribution. So what it's telling us is at this site in the Southern Great Plains, a few events really are dominating damage. Once I have this time series, I can integrate it through time, correct for missing data. We have less than 0.1% of missing data at any of the sites we've considered. And we can get a 15-year accumulated distance to failure and coating lifetime. So has the coating failed within our 18-year period, and how often, or is it longer than 18 years? And that 18 years is just the duration of time for which these observations were available when I started this work. So ta-da, a lot of background there. I hope I haven't bored you too greatly. This map is our erosion atlas, sorry. So the color of the dot and the size of the dot tells us either the 18-year accumulated distance to failure. So if that's more than one, it means it will have failed within 18 years. If it's half, it means it would fail in 36 years. If it's 1.5, then it would fail in 12 years. So the hotter the color, the more erosive the climate is, and the more rapidly that coating would be damaged, and we would start to get material loss, leading edge erosion. So we can see that there are some short blade coating lifetimes here along the Pacific Northwest, along the US East Coast, close to where our offshore lease areas are being built out, and in the center of the country in the Great Plains. The shortest coating lifetime, sorry, that we computed were about 4 years. And just to give you a sense, that's a reasonable order of magnitude. At least one of our major wind farm owner operators does inspections every 5 years. So this would be about the timescale when they might expect to start to see damage. Incidentally, if you'd like to look at the atlas, it's freely available for download from Zenodo here. So please feel free to download it and use it and give us feedback. We welcome it. On the bottom here, what I show is what's the accumulated distance to failure from the top 100 most erosive 5-minute periods. So this is now us trying to look and say, how heavy-tailed is this accumulated distance to failure time series? How focused on a few specific time periods? For our erosive areas, the Pacific Northwest, you can see those top 100 events contribute only about 4% to the total accumulated distance to failure. So not especially heavy-tailed. In the Southern Great Plains, you can see it's up to 15%. So we're starting to see this damage being focused on a few time periods. And the Northeast here, it's sort of in between those two. If you look on the right-hand side here, this is now saying we can look at the top 100, top 200, top 300, 5-minute periods. What is the accumulated distance to failure during those periods? And you can see here the top 100 for a representative site in the Southern Great Plains. It's about 15% of damage that's done in those top 100 5-minute periods in a total 18-year time record. So it's a very concentrated in time. You can see in the Northeast, it's less concentrated. In the Pacific Northwest, it's less concentrated still. So we're trying to get this sense that perhaps in the Southern Great Plains, use of erosion safe mode might be worthwhile because you're only having to stop the turbines for a few minutes per year. Whereas in the Pacific Northwest, we can say damage is occurring over many, many more periods in a year. So perhaps leading edge erosion protection might be a better option in this location. We are cognizant, of course, electricity prices play a major role in this sort of cost benefit analysis. If we now set an arbitrary threshold and we just say for events where more than 1/10 of 1,000th, so one 10,000th of the blade coating lifetime is exhausted in a 5-minute period. When do those occur in a year? So for the Pacific Northwest, again, for the atmospheric scientists, this is no big surprise. It's during our winter months when we have strong mid-latitude cyclones that generate relatively heavy precipitation and high winds. In the Southern Great Plains, our damage tends to be focused on the spring when we're getting deepest convection and heaviest precipitation. So this is a nice sanity check. It's also worth mentioning that highest electricity prices tend to be slightly offset in time in the Southern Great Plains. So we wouldn't be halting our wind turbines during the periods of highest electricity price generally. We can also think about the focus in time, and in the Southern Great Plains, there's more than a 50% chance that a highly erosive period is adjacent to a highly erosive period. So not only are we having to halt the wind turbines relatively infrequently in the Southern Great Plains, sorry, but they tend to be concentrated in time. So it's like stopping the wind turbine for 10-minute periods will extract a substantial number of these damage periods. It's worth saying that because these time series are very heavy-tailed, it does mean we need long time records to get a good estimate of the likely damage. So just here for the Southern Great Plains, you can see here, if I choose a 5-year period drawn randomly from my data set, the most erosive 5-year period gives me a coating lifetime of less than 10 years. The 5 most quiescent years actually give me a coating lifetime of double that. So this tells us if we want to make robust atlases, we really do need these long time series. Oops, sorry. So of course we should say we've released this atlas. We don't begin to suggest it's the final word. It's an initial start. So we can say, what are the uncertainties? We're using a material science model where we can vary those parameters. But our argument is that can lift up or suppress all coating lifetimes in space, but it doesn't have a big effect on gradient. So our hotspot areas would be maintained. We are vertically extrapolating the wind speed. Again, we're going to say it's important to the absolute values, but not the gradients. We assume all droplets impinge on the blade, although we do take account of the fact that the blade is not always perpendicular to the droplets. Based on the DMV standard that's used in wind energy, that impingement probability of 1 is likely to be true. The last two are what I'd like to speak to with the rest of our time together. The first is we're applying an empirical size distribution to our hydrometeors. If we use Marshall-Palmer and we select, for example, a rainfall rate of 15 millimeters per hour and a wind speed of 7, we get an accumulated distance to failure of 0.123 times 10 to the minus 3 in a 5-minute period. If we use the best size distribution, that would be higher by about 50%. So, of course, our accumulated distance to failure estimates are a function of the hydrometeor size distribution. So we need better measurements. We need not to be applying empirical size distributions. Also, we've neglected hail. So again, we need better measurements, and we'll talk about that in just a second. Also, of course, the ASOS network is great, but there are unsampled locations. So I would suggest we also need modeling. And of course, solutions to 4 and 5 might also be useful if we wanted to do short-term forecasting for dynamic operations. So just as we generate forecasts of power production for tomorrow, wouldn't it be great if we could issue a forecast that says, looks like the erosion is going to be bad tomorrow, so perhaps you might want to think about dynamic operation of your wind farm. Or equally, our measurements suggest there's damage or damaging events occurring now. Perhaps you might want to consider dynamic operation. So I suspect that this we won't need to do too much here, except to say for the number density, the hydrometeor number density, we have within the IEA task looked at observational number size distributions, and they do not fit either Marshall-Palmer or the best size distribution. So we do need to be making these types of measurements. There's a lot of interest within this task on the hydrometeor asymmetry. So as you know, if a liquid droplet falls, we change the axis ratio. So essentially it becomes elongated in the horizontal and foreshortened in the vertical. So of course, rain droplets have an axis ratio that's much below 1. And this matters because most of our measurement technologies measure this horizontal axis, not the vertical axis. Hail, of course, doesn't deform. So we need to be thinking about when we're interpreting our measurements, is it liquid or solid? So as you will know, the Department of Energy operate an excellent atmospheric radiation measurement station in Lamont in Oklahoma, and they have 3 types of what we call distrometers operating there. The first is an optical distrometer, which is the type that we also use here at Cornell. And the idea is you have a sheath of laser beams. As the hydrometeors fall, they break the laser beams. The number of beams they break tell you the horizontal diameter of the droplet, and the duration of time that the beam is broken tells you about the fall velocity. Impact disdrometers, essentially as the hydrometeors fall, they record the acoustic noise of the impact here. The assumption is they're falling at their terminal fall velocity, and therefore you can solve for the diameter. And then, of course, there's the 2-dimensional video disdrometers, where you can, using 2 cameras, track individual droplets, characterizing their axis ratio, their fall, their diameter, and other properties. So we did an analysis of couple of years ago here and showed that the rainfall rates from these three instruments are definitely correlated, but they're not perfect analogues for each other. And the number densities that we derive from the different disdrometers are also noticeably different. So we can ask the question, does it matter? And of course, if it didn't, I wouldn't say we asked the question. But when we put the time series of disdrometer measurements into the Springer model, along with wind speeds now from a LiDAR, so no extrapolation is needed, then we can do an analysis that says over 4 years, what's the accumulated distance to failure per year? What's the coating lifetime? If we're using the optical disdrometers, that coating lifetime is not quite double what we get from the impact disdrometer. So it tells us we need to better understand these disdrometers and why they're generating different size distributions, different fall velocities, and so forth for this application. So what we've been doing as part of the IEA task is to explore this lack of closure between disdrometers of different types. So just as a reminder, if we think about the optical disdrometer, what we get is a number density of a size and a fall velocity. So it's a number in a size and a fall velocity class. When we can convert those into our number densities using this equation where F is the field of view, T is the time, V is the fall velocity for a given diameter class, delta DI is the width of the diameter class. If we want to convert them into rainfall rates, of course, it's the cubic dependence on the diameter. So the implication is small errors in diameter reported by disdrometers yield very big errors in rainfall rates, and small errors in either diameter or fall velocity yield big errors in our number density. And a particular area that we're interested in is that we uniformly get these very large, very slowly falling hydrometeors that are present that fall far from our expected terminal fall velocity curve. And in case you're thinking, oh, that's snowfall, snowfall's been removed from this plot, so they are not snowflakes that we're looking at. So why do we get them? So our first hypothesis was a lateral advection. So I'm sorry if I go back. The idea is if the wind is blowing these hydrometeors partly across the plane of these laser beams, they will break too many laser beams, appear too wide, and they'll break them at an insufficiently large fall velocity. So that would be a plausible explanation for this lobe. Second thing is the droplets are not spherical, so there is an assumption being made here about the axis ratio internal to the disdrometers. So maybe those assumptions are wrong, and I'll mention for the laser disdrometers, it plateaus at 0.7, so no hydrometer can have an axis ratio below 0.7, whereas when we do 4 years of analyses of the video disdrometer, we would suggest that actually the axis ratio can be much smaller. It's a splash from instrument casing where it hits the case and falls into the viewing angle, or are there cases where the lasers are misaligned? What are we doing? Well, sorry, before I go on to that, I should say, if you're from the atmospheric science community like me, usually we process disdrometer data and we say if it falls outside of if a droplet is falling outside of our expected bounds around the terminal fall velocity from Gunn and Kintzer, so if we do plus or minus 50%, sorry, plus or minus 60%, then we throw it away. We say it is an erroneous measurement. It's worth noting if we do that at the arm site in Southern Great Plains, we're saying 24% of observations are wrong. That's a really large fraction of the data we are excluding. So we wanted to go back and say, is it really right that 24% of these observations are in fact incorrect? So we've done some explorations. The first one was buying 4 of these laser distrometers, taking them out of the box, putting them up within a meter of each other and looking for closure. And what you can see here is that the average droplet size distribution from one of the distrometers was noticeably discordant with the other 3, and that led to a positive bias in rainfall rates of above the plus or minus 10% the instrument is certified for. So our first recommendation is before you put out a distrometer network, you need to do closure experiments to check that there isn't a misalignment of the laser, because a very small misalignment leads to very rapidly growing errors. The other thing we've done is deploy one of our distrometers shielded with a windshield, one of them open with a view to saying, does the shielded distrometer stop reporting these slowly falling large droplets? The answer is no, at least for our moderate wind speeds, we didn't find that it removed these erroneous data. So what we're doing is trying to explore distrometer closure experiments, distrometer deployment strategies, and then doing individual case studies where we see distrometers disagreeing to try and better understand this performance issue. Very quickly, we've also been looking at using numerical modeling, both in the context of filling in space where we don't have measurements, but also in a predictive context. So I'll just show you 2 results. One is where we ran WRF in a pseudo climate mode. So we ran 9 months of simulation, from 2017. The inner domain here is shown discretized at 1.3 kilometers. The red dots are wind turbines operating within that domain. By climate mode, we're using ERA interim lateral boundary conditions to force the domain 1. We're doing 14-day cold restarts. We're not doing any nudging and we're not doing data assimilation. So we're trying to say, if we ran this model in a quote climate mode, how well will it run? We use the Milbrandt-Yau microphysics scheme. So I've just for fun here pulled out some videos that we made here comparing radar. So we've built our own composite of radar from 9 radar within our simulation domain. So we've got composite reflectivity, rainfall rate, presence of hail, and then the time series. I'm trying to persuade you here simply that these simulations have some fidelity. They are correctly capturing deep convection, for example. But of course, we've got the space-time penalty, and that's particularly important to us when we think about erosion. So again, if we use the DOE ARM site for validation, we can say, well, so we've got heat maps here on the x-axis, the wind speed in different classes, on y-axis, the rainfall rate. You can see here that rainfall rates around 5 to 15 millimeters per hour are relatively common in the observations and are undersampled, of course, in WRF, not least because of the spatial averaging. So what does this tell us? That we have done a single configuration, we'll be frank. the good fidelity was found. I didn't show it to you, but for wind speeds at most of our stations. So we capture the wind climate relatively well. We capture some aspects of these intense, heavily precipitating and hail-rich events, but of course, we have a massive penalty if the precipitation is slightly displaced in time or space. We lose the ability to compute erosion. The other thing, at least for our Milbrandt-Yau simulations, were that we underestimated the maximum estimated size of hail relative to our 9 radar observations. So essentially, WRF seemed to collapse that maximum estimated size of hail into a much smaller range than the radar report. So that would tend to lead to a negative bias in our erosion climates. Last but not least, last slide, Sue, don't worry, you don't have to drag me off with a hook. We've also been doing some storyline events where we're trying to explore multiple microphysics schemes, and we're using this in a kind of short-term forecasting mode where we're using lateral boundary conditions from the rapid refresh model. We're doing 1 day ahead. We are still not using nudging or data assimilation because we wanted to examine the inherent sort of characteristics of the microphysics schemes. This is one event, sorry, just to locate you, the triangle is Dallas-Fort Worth. This was an area of deep convection that came over the wind farms to the north of Dallas. So it's an interesting case. Even when we average over this entire inner domain, you can see here the rainfall rate for all of the 5 microphysics schemes we tried was actually overestimated for this case. It's not always true. The accumulated precipitation is also overestimated. And you can see here, we've got an enormous spread. Even if we try and get rid of the time-space penalty, by doing a domain-wide integrated precipitation amount. What are we trying to do here? We're trying to build a coalition to actually undertake a comprehensive evaluation of WRF and possibly advance an optimal configuration. So trying to say, if this model is going to be employed in this use case, how would we recommend it be configured and run? And I think we also need to build a slightly more comprehensive and robust model V&V framework that really addresses this issue of needing fidelity for the joint probabilities or the cupola, rather than thinking about skill for individual variables, which I think certainly within the atmospheric science community, we've tended to focus on more. We face a big challenge. It's an exciting research topic, I think. From my perspective, collaborations and questions are most certainly welcome. Thanks very much for your attention.
Virtual applause. Yay. Thank you, Sarah. Excellent seminar. Okay, for the Q&A, I invite you to raise your hand, look on the little react button on the bottom, and you'll see that there's a raise hand function, and then unmute and ask your question. Or if you have a question, feel free to just type it in as well, and I'll be glad to read it. So Sarah, this is really fascinating. I do report that I have been able to download your 2025 paper that some of this is based on already. So Dan, it looks like you have a question.
Thanks so much, Sarah. That's like just an amazing talk. I really love how we blended together so many scales and levels of analysis. From the microphysical to the economic. I'm wondering on the sort of on the higher abstraction level, what you know about existing sort of bespoke technology to handle this in the field? Are there a lot of I mean, presumably folks who operate big wind farms in the Central Great Plains have thought about this a little bit. Are there currently algorithms in place to turn off wind farms during high rain events?
No, no, we've actually been trying to actually work with the Danes, because they did manage to convince a wind farm to curtail during highly erosive events. So they had micro rain radars out at the corners of the wind farm. And I think for a very short period, they did dynamically operate the wind farm. But at the moment, we're not aware of anybody dynamically operating to try and reduce erosion. The wind farm that a big major wind farm owner operator that they spoke to, that we spoke to, sorry, said that they did not yet feel that they had confidence that the loss of power production would be worth the blade coating lifetime extension. So it's what we've done is we've tried to release the atlas, send it out to owner operators and say, shoot it down. Interestingly, the greatest interest we've had is actually from LEP providers. So leading edge erosion protection providers that think this is a market opportunity.
Oh, that's interesting, because I mean, my first reaction to that was going to be, well, is it possible that the reason is that people are just using are doing enough maintenance that they're not seeing huge long-term losses, and that the main opportunity here is that they could do less maintenance if they could save money on maintenance if they just curtail during high rain events? Is that possible, or what do you like? Or are we seeing? Do you think there's a lot of fast? I mean, I first heard about this as an issue of faster than expected erosion in like Danish wind farms and offshore wind farms. Oh my gosh, this is the big deal. No one was counting on this. It's going to make these plants much more expensive. But is that a story that you're hearing across the places like the Central Great Plains?
Yeah, the only owner operator that we've talked to have said that based on the atlas, they may move away from just saying every 5 years at every wind farm we inspect, but actually trying to make that a little bit more location specific. You're right that a major offshore owner operator in Europe did in fact remove blades, take them back to the shore and apply protection.
Yeah.
And we don't want that in the US, do we? And you'll see this northeast is actually the closest ASOS station to the Massachusetts lease area, and it's suggesting that it's a pretty erosive climate out there.
Yeah.
So
Okay.
we hope, we released the atlas, quite frankly, 2 weeks ago. We've had some people contact us about it. Let's hope it's useful. And if it's not, I think it's still okay, because hopefully we can get some feedback that says, we don't like the way you formulated it. Can you do it differently?
Yeah, I don't know if anyone else from EPR is on the call, but I will definitely get the recording of this in front of our wind group and make sure we're having conversations with our members about it, because it seems like
yes, the recording should be posted later this week. And like I say, the most recent paper is easily downloadable. I found it quickly. Virendra had a question. He had your hand up. Do you still have a question, Virendra?
I do have a question. Fantastic talk. Really nice. Blended a lot of material, a lot of work going on in here. My question is, I always thought that the particles fall not with the fall velocity within the beam, the distorted beam, because of turbulence, because they can caught in an updraft or downdraft. You have that. So have you looked into that? That if the turbulence is causing that thing, or just something else, or just not the sort of slanting of the particles?
Yeah. So it's a great point. So what we're trying to do, actually with the DTU group, is to deploy disdrometer with some sonics around it to try and get a sense of, you know, the heads are going to generate turbulence, and I suspect there's not that terribly much we can do, but whether we're getting turbulence generated by other things around the disdrometer and whether we can correct, in principle, correct for that. The sort of long the long term is we wish the manufacturers would be a bit more open about what they're doing, because they are performing internal corrections that are not very explicit, and I think we need to be a bit more, hopefully, transparent and just understand what's really being done. But you're right, we've got this experimental design that we're trying to implement to try and say what are the turbulence regimes around the head. We had this great idea we would use a LiDAR, but we can't make the beam narrow enough to actually look at the field of view.
Okay, fantastic. It's a hard problem. And the other question I had is, I like that you found fantastic, like the um, the erosion in the North Pacific Northwest and the Northeast is kind of a slow burn. You get this slow all the time, and then SGP will have just a boom. You get that. Can you talk about the minimum diameter of the drops that is actually causing the most frequently you observe, and that is causing the most erosion? Because that will determine, because stratocumulus you basically get many different. So if I understand correctly, about you start about quarter of millimeter, right? 250 micron, if I understand correctly, right? But what was the
Yes.
reason for that? Just wondering.
Yeah, so one of the things that we've actually just started to do is to try and say, instead of thinking about these heat maps in terms of rainfall rate, to actually add another dimension and say, okay, so what's the effect, you know, what's the diameter that's really driving this? I can say we haven't done it, but we should have done it. We should have added a third dimension, and we're trying to.
Okay. People
Good
always
point.
ask. But thank you. Thank you very much.
Okay, we'll take one more question. It's typed here. Majed Al-Rashidi from Kuwait comments, I wonder whether a similar study might be conducted on the effects of sandblasting on wind turbine blades due to sandstorms in desert environments, since there's a high potential of deploying wind energy in hot desert regions, as I know they are in Kuwait. Any comments, Sarah?
Yeah, actually, within the IEA task, we tried to obtain data about, I'm going to say dust, sand, from satellite observations to try and think about sandblasting. I can say it's a bit nascent. Most of the lab studies that have been done have focused on hydrometeors and not sandblasting, but it's certainly true that you could certainly envisage sandblasting as being important. So maybe I should have said anybody can join this IEA task. If you look up IEA task 46, there's a formal application process, but I believe it is globally, it's global, it's international, and I think we would welcome more participants. So if you Google it and you don't find it, please email me and I'll send you the information to join.
Okay, let's all thank Sarah one more time. And we really appreciate the seminar, a really good use of an hour. And I put the link where the recording will be posted later this week. Thank you, everyone, and see you next month. And I believe it is also on March 12th. So looking forward to the next one as well. Bye-bye.
Bye. Thanks very much, Sue.